5.5 Sample Problems from the Law of Sines, DeMana, Edition 7. In problem 7, we are given that A equals 33 degrees, B equals 70 degrees, and little b, the side, equals 7. The first thing to do is to draw roughly a triangle of what this might look like. And I've drawn A of 33 degrees, B of 70 degrees, and a little side B here of 7. The accuracy of the triangle is not important, but it is important to get the perspective across that the side B across from it 7 is the angle B, and across from the angle A is the side A, across the angle C is the angle C. The triangle is just a rough idea to help me keep those straight. Now, from the law of sines, we know that the sine B over B, and those are the two things we know. So start with what we know, is equal to sine A over A. Let's solve for little a because we know the big angle A. We solve for A and we get that equal to the sine of A over the sine of B times the side B. That's going to be equal to the sine of 33 degrees, sine 70 degrees multiplied by 7, and that comes out to 4.3. Angle C is straightforward. There have to be 180 degrees in any triangle, so it is 180 degrees minus the two angles we know, 33 degrees minus 70 degrees. That makes the angle C 77 degrees. Now, we now want to solve for little c, this side right here. We could equate it to A, sine A over A, which we solved, but remember that's an approximation. So always go back to the one to which you know exactly, which would be B. And we go back to B to solve this. And so we know that sine B over little b will be equal to sine C over little c. Little c is what we're solving for. So little c, lowercase c, is equal to the sine of the angle C over the sine of the angle B times B. That will be equal to the sine of 77 degrees over sine of 30 degrees times B, which is 7, and that comes out to be equal to 7.3. And those are the other three pieces of the triangle. In problem 22, we have B equal 57 degrees, A equal 11, and B equal 10. Again, this is an SSA side triangle. And this particular one is ambiguous. Look how it can be drawn. I've drawn B here at nominally 57 degrees. The side opposite 10. But the side of A would be 11. It does not matter which one I call A and which one I call C. It just would have been drawn slightly differently, but it would have had the same problem. But since this side is 10 and it is shorter than this side, that permits me to swing it back underneath and form another triangle here in which B is still 57 degrees. And the two sides are the same. But now this is an obtuse angle here at A, where in this case A has an acute angle. Those are the two triangles we want to solve. Let's look at the first triangle. We have sine B over B is equal to sine A over A. So that the sine of A is equal to A over B times the sine of B. Angle A is equal to the arc sine A over B sine B. This is the arc sine of 11 over 10 times the sine of 57 degrees equals 67.3 degrees. Angle C would then be 180 degrees minus 67.3 degrees minus B, which was 57 degrees. That's equal to 55.7 degrees. Then again, for C, we have sine B over B is equal to sine C over little c. We solve for little c, and that will be equal to the sine of the angle C over the sine of the angle B times B. When we put those numbers in, we get 9.9 degrees. Now let's look at the second triangle. In the second triangle, this angle A is obtuse. But look what we did. We took this, which was determined here, A, to be 67.3 degrees, and we moved it back inside. So this angle is 67.3 degrees, but when we move it back inside, this angle is also 67.3 degrees. This total angle is 180 degrees. So that makes this obtuse angle in the second example here, we could call this A2, is equal to 180 degrees because of this 180 degrees minus 67.2 degrees, which was the angle that we got on this side, 67.3 degrees. So 180 degrees minus 67.3 degrees makes the obtuse A 112.7 degrees here. Let's draw the triangles again. Now we've redrawn the triangle, made it a little bit larger so we can see it. Now we solve for the angle C. Let's make it a 2, since this is our second triangle. C2 would be 180 degrees, the number of degrees in the triangle, minus 57 degrees, which is angle B, minus 102.7 degrees, which is angle A. And that would be 10.3 degrees. Finally, we find this little side here, which we can call little c2. So we have sine of b over b is equal to the sine of angle c2 over little side c2. Little side c2 is equal to sine of angle c2 over sine of b, it did not change, times b. This is equal to the sine of 10.3 degrees over the sine of 57 degrees times 10. So that little c2 is equal to 2.1. In problem 27, we're asked to decide if we can decide the triangle. So I drew angle A equals 61. A would be 8, and call this angle B, would be 21. In this case, two things can happen. Side 8 could be drawn this way or this way, so therefore we would have to say that this triangle is not solvable. Note again that this is the SSA case, which can be ambiguous, and in this case it is. We could solve for both triangles, but we cannot say what triangle is assumed here. In problem 42, a Ferris wheel has 16 evenly spaced cars. The distance between adjacent cars is 15.5 feet. What is the radius of the Ferris wheel? Here we have drawn the Ferris wheel. And here are the distance between cars. This distance is going to be 15.5 feet. In this case, we have drawn one of these sections of the triangle. And we call this angle C and this angle B on each side, going into the radius here, and we're going to call that side A. First of all, there are 16 evenly spaced cars. They have to go around and make an angle of 360 degrees. So A will be 360 degrees divided by the 16 cars, making A 22.5 degrees. A, B, and C add up to 180 degrees. B and C have to be the same, in spite of the fact that my picture looks a little distorted. But B and C are the same because it's evenly divided. So B or C would be represented in this way. Let's just say 2B for a second, let B equal to C. So 2B is going to be 180 degrees minus 22.5 degrees, the value of A. So B is going to be 1/2 of 180 degrees minus 22.5 degrees. That's also going to be equal to C, equal to 78.75 degrees. Now let's draw it again. Now we've redrawn the triangle. Mark the angles we discovered, and side A is 15.5 feet. So let's solve for either little b or little c. Using the law of sines, we have the sine of A over A is equal to the sine of B over B. B is equal to sine B over sine A times A. Sine of 78.75 degrees over the sine of 122.5 degrees multiplied by A, which is 15.5 feet. Gives us an answer of 39.7 feet. This is also C, since both sides B and C are the same, and this is an equilateral triangle. So, since any of these represent the spoke, we now have the radius of the wheel at 39.7 feet.